Hello, my name is Saúl Javier Domínguez León. I'm from to Universidad Juárez Autónoma de Tabasco, and I'm going to tell you about the preparation of Mesoporous membranes based on silica composite hells for gas permeation. This paper presents the process and developing silicon dioxide membranes using a salt hell technique. The hells will formulate with the goal of producing a stable solution containing citric acid, nitric acid, water, and tetraethyl orthosilicate, and alkoxide used as silicon source. In addition, two types of membranes were fabricated using ethanol and methanol. This dual approach aimed to ensure pore formation and investigate the influence of alcohol chains on pore size. The resulting solution solidified over a 24 hours period at a consistent 60 degrees centigrade temperature. Subsequent to hell formation, they were introduced into a vacuum driver oven where the temperature was maintained below 30 centigrades. This step facilitated the removal of residual water and alcohol, while also enhancing densification. Following this, obtained membranes underwent a sintering process to encourage crystallization. The membranes were time subject to comprehensive characterization using techniques such as X-ray diffraction, after-year spectroscopy, and scanning electron microscopy. These methods enable to identification of crystalline structures, analysis of gas permeation signals, determination of pore dimensions, and evaluation of surface morphology, respectively. To conclude the study, gas permeation tests were executed using hydrogen, nitrogen, oxygen, and pollutant gases like the oxygen carbon. These tests aim to ascertain the potential suitability of the membranes for gas separation applications. Gas diffusion through the membranes transpires via the pores formed within them. These pores being sufficiently minute to facilitate the passage of the most gas, including hydrogen, contingent upon the molecular size. Gases of larger dimensions, such as nitrogen and oxygen, encounter obstruction. The egress pressure exhibit a correlation with elevated entry pressures. Conversely, under dimension pressures, the membrane will sustain a 90% permeation rate for hydrogen, whereas the passage of nitrogen and oxygen will be greatly restricted. This attribute renders the membrane apt for the segregation of gas mixtures tailored for specific objectives. In the figure 2, the permeation setup comprises four distinct stations. The first stations serve as the point of entry for the gas facilitated by respective gas cylinders containing hydrogen, nitrogen, oxygen, and dioxide carbon. The second station is equipped with an Arduino pressure sensor responsible for monitoring the inlet pressure. The third station features the permeation chamber, seamlessly connected to the gas cylinder, and serves as the locus of permeation. Following this, the gas outlet constitutes two four stations characterized by a depressurization valve and an Arduino pressure sensor. The latter transmits signals to the final station, which involves data presentation on a monitor. The permeability coefficients were determined by establishing a correlation between the most elevated and lowest pressures observed for each membrane, corresponding to the gas that underwent formation. This correlation was then multiplied by the constant thickness of the membranes, which in this instant remained consistent at 180 micrometers. In figure 3, the scanning electron microscope micrograph showcases the morphology of each fabricated membrane. Notable, the membrane synthesized with methanol stands out as the most promising evidence from the discernible improvements in this characteristic. The micrograph revealed a noticeable distinction in pore size between the methanol derivative membrane and its ethanol counterpart. This distinction can be attributed to ethanol's elongated molecular structure, resulting in the formation of larger pores. The finding revealed that there were two primary stages present in the spectra, namely the cristobalite and tridimide phases. These phases align with the most prominent peaks observed in the display diffraction patterns. The FTIR spectrum of silicon dioxide is depicted in Figure 5. It's evident that the brown band around the 3440 inverse centimeters corresponds to the oxygen-hydrogen stretching abbreviation resulting from the condensation of silanol groups, as well as the presence of adsorbed water. In Figure 6, the permeation results are visually presented by plotting the permeability coefficients against pressure in PSI over a duration of 60 seconds for each of the two membranes. The data showcased in this graph provided valuable insights into the behavior of gases as they permeate through two membranes. Uh, Silicon dioxide and methanol membranes manage to permit a greater amount of hydrogen in the pressure range of 5 to 30 psi, thus having lowered all the pressures in oxygen and nitrogen, which means that the pore size is adequate for the permeation of hydrogen. On the other hand, silicon dioxide ethanol membranes give free passage to the oxygen and nitrogen gases, so their use is not viable. All this due to the addition of alcohols. Methanol generates smaller pores useful for hydrogen permeation. Therefore, gas separation may be possible considering the selectivity of the membranes and using methanol to have a smaller pore size. XRD and FTIR results verify silicon dioxide formation and evidence of a condensation reaction of silicon and oxygen groups at the time of permeation testing. The permeation system used is convenient due to the incorporation of Arduino sensor, which measures second by second the inlet and outlet pressures, and thus have more accurate data. Thanks.